close your eyes for a moment and picture the sun. Go on. The image is already there, waiting. A calm yellow disk, a steady, reliable light that rises every morning and sets every evening. The same today as it was yesterday, the same as it will be tomorrow. It is. In the story most of us carry around without ever examining it, the most dependable thing in the sky, the one constant, the clock, the rest of the universe sets itself by. That picture is comforting. It is also almost nothing like the truth. The sun is not a calm yellow disk. It is not even, strictly speaking, yellow. That's a trick of our atmosphere. Step outside Earth's air, and the sun burns a blinding, furious white. It is not steady. Its surface is not really a surface at all, but a churning, boiling skin of plasma 1,000,000 kilometers deep, laced with magnetic fields so angled and so violent that they periodically snap like overstretched rubber bands, releasing more energy in a single instant than humanity has produced in the whole of its recorded history. It is not reliable in the way a clock is reliable. It is reliable the way a sleeping animal is reliable. Mostly quiet, mostly predictable, until, without much warning, it isn't. We have built an entire civilization underneath this thing. Our power grids, our satellites, our navigation systems, our communication networks, the unseen electronic nervous system that keeps modern life running, all of it sits exposed beneath a star we have chosen, culturally, to imagine as gentle. And every single day, that star is doing something almost too strange to believe, converting 4 million tons of its own mass into pure energy every second through a process so inefficient that, gram for gram, the core of the sun produces less heat than a compost heap, and yet it is so vast that this trickle of a reaction can flood an entire solar system with light. Tonight, we are going to take that comfortable picture apart, piece by piece, and look at what's actually underneath it, not to frighten you, though some of what you're about to hear may do exactly that. But because the real sun, the one revealed by more than a century of careful, patient, occasionally desperate science, is so much stranger, so much more violent, and so much more alive than the one hanging quietly in your imagination. The sun isn't what you think. It's worse. And it's more magnificent than you ever gave it credit for. Let's begin. The comfortable story we tell. For nearly the whole of human history, the sun was not a scientific object at all. It was a god, or the eye of a god, or the chariot of a god dragged daily across the vault of heaven. The Egyptians called it Ra and imagined it sailing a boat through the underworld each night to be reborn at dawn. Greeks gave it Helios, driving a blazing chariot from one horizon to the other. And priests believed the sun required nourishment, human nourishment, to keep rising. Across almost every culture that ever looked up, the sun was treated the same way, as the one thing in the universe whose continued good behavior could not be taken for granted and had to be earned. There is something almost quaint about that anxiety now, in an age when we assume the sun simply switches on every morning without ceremony. But it's worth sitting with the fact that our ancestors, without a single instrument, without any physics at all, intuited something modern civilization has quietly forgotten: that the sun's steadiness is not guaranteed. It has to be understood, respected, watched. For most of the history of astronomy, understanding the sun meant almost nothing beyond charting its position. It was too bright to look at directly, too close to study the way distant stars could be studied, hidden behind its own blinding glare, like a stage lit so brightly you can't see the machinery producing the light. Galileo, pointing one of the first telescopes at the sky in the early 1600s, became one of the first people in history to notice dark blemishes moving across the sun's face, sunspots, and was roundly criticized for suggesting that the supposedly perfect, unchanging heavens could have blemishes at all. The idea that the sun might be flawed, dynamic, imperfect, was, for a moment in European intellectual history, genuinely heretical. It took another 3 centuries before anyone could offer a halfway convincing explanation for what actually powers the thing. 19th century physicists, working with the tools available to them, tried gravity. Perhaps the sun was slowly collapsing under its own weight, converting that collapse into heat, the way friction converts motion into warmth. Run the numbers, though, and the sun would burn out in a few tens of millions of years. A serious problem for a 19th century that was simultaneously discovering, through geology and the newly minted science of evolutionary biology, that the Earth itself was almost certainly far older than that. Something didn't add up. The sun was radiating far more energy for far longer than any known physical process could explain. The answer wouldn't arrive until physics cracked open the atom itself in the first decades of the 20th century and discovered a source of energy so concentrated, so far beyond anything in ordinary chemistry, that it barely seemed to belong to the same universe as fire or friction. That discovery didn't just explain the sun. It rewrote what the sun fundamentally is. Not a ball of burning gas, in any sense a candle or a campfire would recognize, but something closer to a very slow, patient, very carefully contained bomb, 4.5 billion years into a controlled detonation that has been running without pause since before there was an Earth to warm. That's the story most of us never got past in school. Sun equals big fireball equals light and heat. End of chapter. It's not wrong so much as it's dramatically, almost comically incomplete. The astrophysical equivalent of describing a symphony orchestra as a room full of noise. What's actually happening inside the sun, once you look closely, turns out to be one of the strangest, most delicately balanced, and most quietly dangerous processes in the observable universe. And the first step towards seeing it clearly is understanding just how badly burning describes what's really going on. The impossible furnace, say the word burning, and most of us picture combustion, the chemical reaction that turns wood or gasoline or coal into heat and light by breaking molecular bonds and forming new ones, releasing a modest amount of energy in the process. If the sun burned the way a fire burns, using ordinary chemistry, it would run out of fuel catastrophically fast, within a few thousand years. By some early calculations, nowhere close to the billions of years geology demanded. Whatever the sun is doing, it isn't burning in any sense a chemist would recognize. What it's actually doing is fusion, and fusion operates on a completely different scale of violence. Deep in the sun's core, under pressures roughly 250 billion times what you feel at sea level on Earth, and at temperatures around 15 million degrees Celsius, hydrogen nuclei, single protons, stripped of their electrons in the crushing heat, are forced together with enough force to overcome their mutual electric repulsion. Two positively charged protons do not want to touch. Left to their own devices, under any conditions found on Earth, they would repel each other with tremendous force and never come close enough to interact. Inside the sun's core, gravity supplies pressure so extreme and temperature so extreme that protons are slammed together anyway, hard and often enough that Occasionally, something extraordinary happens. Two of them fuse. The specific pathway is called the proton-proton chain, and it unfolds in careful, almost bureaucratic stages. Two protons fuse into deuterium, releasing a positron and a neutrino in the process. One of the protons essentially transforming into a neutron as it goes. That deuterium nucleus then captures another proton, forming a light isotope of helium and releasing a burst of gamma radiation. Finally, two of those light helium nuclei collide and fuse into ordinary helium-4, spitting two leftover protons back out to begin the cycle again elsewhere. At the end of this chain, 4 hydrogen nuclei have become one helium nucleus, and the helium nucleus weighs very slightly less than the 4 hydrogen nuclei that built it. That tiny missing mass is the entire story. Einstein's famous equation, energy equals mass times the speed of light squared, tells you exactly what happened to it. It didn't vanish, it converted. And because the speed of light is such an enormous number, even a vanishingly small amount of mass converts into a staggering amount of energy every second. Inside the sun's core, roughly 4 million tons of matter, the mass of a small mountain, simply stops existing as mass and reappears as energy. This has been happening for 4.5 billion years. It will keep happening, more or less unchanged, for roughly 5 billion more. What holds this entire furnace together, keeps it from either collapsing under its own crushing gravity or blowing itself apart in an instant, is a balance so precise that physicists gave it its own name: hydrostatic equilibrium. Gravity is constantly trying to crush the sun down into a smaller, denser object. The outward pressure generated by fusion, both the raw thermal pressure of superheated plasma and the outward push of radiation itself, is constantly resisting that crush. Two forces are matched to a degree of precision that would be almost impossible to engineer deliberately. And the sun has maintained that balance, self-correcting automatically, for the entire span of its existence. Squeeze the core slightly and fusion speeds up, pushing back harder. Let the core expand slightly and fusion slows down, letting gravity regain the advantage. It is, in effect, its own thermostat, a self-regulating nuclear reactor roughly 1.5 million kilometers across, running unsupervised, with no operator, no off switch, and no safety manual, for longer than complex life has existed on the planet it warms. And yet, and this is where the comfortable picture starts to genuinely crack, this furnace, for all its violence, turns out to be almost absurdly inefficient. The sun does not generate its heat quickly. It generates it in the slowest, most grudging way imaginable, and the reason why takes us even deeper into the strangeness of the sun's core. The slowest furnace in the universe. Here is a fact that surprises almost everyone who hears it for the first time. Pound for pound, volume for volume, the core of the sun generates less heat than your own body. It sounds absurd on its face. The sun's core sits at 15 million degrees Celsius, hot enough to vaporize any material known to physics instantly and completely. Your body sits at a gentle 37. And yet, if you compare the actual rate of energy production, watts generated per cubic meter, the sun's core produces roughly the same amount, watt per watt, cubic meter for cubic meter, as a compost heap slowly decomposing in someone's backyard. Some comparisons put it even lower, closer to the metabolic output of a resting reptile. The sun isn't a furnace in the sense of something raging and intense per unit of material. It's barely simmering, reaction by reaction, atom by atom. reason the sun manages to produce the almost incomprehensible total output it does. About 8 times 10 to the 26th watts. Enough energy released every second to satisfy humanity's entire current energy consumption for roughly 500,000 years. Comes down entirely to scale, not intensity. The sun's core alone holds a volume vastly larger than the entire Earth. Multiply an almost embarrassingly modest rate of energy production by a volume that enormous, and you get an output so large it beggars ordinary language. It's less like a bonfire and more like an entire continent of smoldering peat bogs, each one barely warm to the touch, adding up across an unimaginable area to something that lights a solar system. The proton-proton fusion reaction itself is also on the level of individual particles, almost comically unlikely. The initial step, 2 protons fusing into deuterium, depends on a process called quantum tunneling, the same effect that lets particles slip through energy barriers they classically shouldn't be able to cross, even under the sun's crushing core pressure. Any individual proton has an extraordinarily small chance of fusing with another proton in any given moment. Estimates suggest a single proton in the sun's core will, on average, wait around 10 billion years before successfully fusing at all. The sun works not because any individual reaction is likely, but because there are so many protons colliding so many times per second in a core so vast that even a reaction this improbable happens often enough in aggregate to power a star. And then there's the part of this story that sounds like it belongs in a piece of speculative fiction rather than a physics documentary. The light being generated in the sun core right now, this instant, is not the light reaching your eyes today. Photons produced by fusion deep in the core don't travel in a straight line to the surface at the speed of light and burst out 8 minutes later. They are born into an environment so dense, so thick with charged particles that they are absorbed and re-emitted, over and over, bouncing in essentially random directions each time, in a process astrophysicists call the photon random walk. Estimates for how long an individual photon takes to blunder its way from the core to the surface, a distance of roughly 700,000 kilometers, vary considerably depending on the model, ranging from tens of thousands of years on the low end to well over 100,000 years on the high end. Whatever the precise figure, the underlying point stands, and it is genuinely staggering. The sunlight warming your skin today began its journey inside the sun's core some time before the last ice age fully receded, possibly before modern humans had finished spreading across the globe. Only the final 8 minutes of that journey, the trip across the vacuum of space from the sun's visible surface to Earth, happens anywhere near the speed of light. Everything before that is a decades to millennia-long traffic jam of light, trapped and jostled inside its own star, patiently working it way toward daylight. The neutrino problem. If photons take tens of thousands of years to escape the sun's core, there is exactly one mess that doesn't wait around at all. And for several decades, that messenger nearly convinced physicists that something was fundamentally, catastrophically wrong with their entire understanding of how stars work. Neutrinos are produced directly, in vast numbers, by the fusion reactions in the sun's core, and unlike photons, they barely interact with matter at all. Where a photon gets trapped and bounced for tens of thousands of years, navigating out through dense solar plasma, a neutrino created in that same instant simply passes straight through the sun, through the whole 300,000-mile diameter of it, in about 2 seconds, essentially unimpeded, because neutrinos neutrinos interact with ordinary matter so weakly that the sun, despite its almost inconceivable density, is functionally transparent to them. They arrive at Earth roughly 8 minutes later, alongside the sunlight from that very same moment, but having taken an entirely different, nearly instantaneous route out of the star. This made neutrinos, at least in theory, the single best tool physicists had for peering directly into the sun's core in real time. A live, unfiltered readout of what fusion was actually doing right now, rather than a hazy echo, delayed by tens of thousands of years. In the late 1960s, physicist Raymond Davis Jr. built an enormous detector nearly a mile underground in a South Dakota gold mine. A massive tank filled with hundreds of thousands of gallons of cleaning fluid, shielded by all that rock from cosmic ray interference, designed to catch the vanishingly rare instances when a solar neutrino would actually interact with an atom inside the tank. The detector worked. It caught solar neutrinos, but it caught far fewer than theoretical models of the sun predicted. Only about a third of the expected number. A discrepancy that held up, stubbornly, experiment after experiment, for decades. This became known as the solar neutrino problem, and for nearly 30 years, it sat as an open, unresolved wound at the heart of astrophysics. Either the standard model of how the sun generates energy was subtly wrong, or the standard model of particle physics, which had, up to that point, assumed neutrinos were essentially massless and came in one single unchanging type, was wrong instead. Neither option was comfortable. Both had been built on decades of otherwise successful, well-tested science. The resolution, when it finally arrived at the turn of the millennium, turned out to be genuinely beautiful and genuinely strange. Neutrinos, it emerged, come in 3 distinct types, called flavors, and, crucially, they can spontaneously shift from one flavor to another as they travel, a phenomenon called neutrino oscillation. The sun's core produces one specific flavor almost exclusively. Davis's original detector, and others built on similar principles, were only sensitive to that one flavor. By the time solar neutrinos reached Earth's surface, a significant fraction of them had oscillated into the other 2 flavors along the way, invisible to the detectors that were only looking for the original type. The Sudbury Neutrino Observatory in Canada, using a detector sensitive to all 3 flavors simultaneously, confirmed the total neutrino count matched theoretical predictions almost perfectly once all 3 flavors were counted together. The sun had been right all along. It was our understanding of the neutrino itself that had been incomplete. It's worth pausing on what that resolution actually represents, because it's easy to let it pass as a tidy footnote. For 30 years, some of the most careful, rigorous scientists alive stared at a stubborn discrepancy between prediction and observation and had no idea, going in, whether the flaw sat in the astrophysics of stars or in the fundamental particle physics of the universe itself. Building detectors a kilometer underground, waiting years for statistically significant data, and ultimately discovering an entirely new property of one of nature's most elusive particles to close the gap. The sun, it turned out, had been sending an honest, accurate signal about its own core the entire time. We simply hadn't yet built the right kind of ear to hear what it was actually saying. A surface that isn't a surface. When you look at the sun, never directly, and only ever through proper filtered equipment, what you're seeing is called the photosphere, and the word is worth taking apart because it means, roughly, sphere of light. It is not a surface in any sense a geologist would recognize. There is no solid ground, no boundary you could stand on. The photosphere is simply the layer at which the sun's plasma finally becomes thin enough, after all those tens of thousands of years of the photon random walk, for light to escape freely into space, rather than being immediately reabsorbed. It is a surface of transparency, not a surface of substance, the point where fog finally thins enough to see through, rather than a wall you could touch. Look closely at that surface, with the right instrument, and it does not appear smooth at all. It looks almost like the surface of a pot of boiling oatmeal, seen from directly above, magnified to a planetary scale. A mottled, constantly shifting texture called granulation. Each individual granule is a convection cell, a column of superheated plasma, rising from deeper inside the sun, spreading out, cooling slightly, and sinking back down at its edges in a cycle that repeats every 8 to 20 minutes. Any single granule, however, is not small by any human standard. A typical one spans roughly 1,000 kilometers across, wider than many countries, and the entire visible surface of the sun is tiled, edge to edge, with millions of these cells, each one rising and dying, and being replaced in the time it takes you to make a cup of tea. Scattered across this boiling, granulated surface are the sunspots Galileo scandalized his contemporaries by describing: regions that appear darker than their surroundings. Though dark, here is deeply relative. A sunspot, isolated from the rest of the sun and viewed on its own, would still be blindingly bright by any earthly standard. It only looks dark by contrast with the even more intensely luminous plasma surrounding it. Sunspots form where powerful, concentrated bundles of the sun's magnetic field punch up through the photosphere, and that intense local magnetism actually suppresses the convection that would otherwise carry heat up from below, which is why sunspots run several thousand degrees cooler than the surrounding surface, dark islands of relative calm sitting in a sea of violence. Sunspots are not permanent features. They form, grow, sometimes merge with neighboring spots, and eventually dissolve, over periods ranging from days to a few months. But they are far from random in their behavior. Careful, centuries-long records of sunspot counts revealed something remarkable. Their numbers rise and fall in a rhythm, cycling from a quiet minimum, when the sun's face may go days or weeks with no visible spots at all, up to an active maximum, when dozens can appear at once, and back down again over a period that averages roughly 11 years. This is the solar cycle, and it is one of the sun's most reliable rhythms, reliable in its overall periodicity, at least even if the intensity of any given cycle and the precise timing of its peaks and valleys remains stubbornly difficult to predict in advance. Underlying the sunspot cycle is something even stranger. The sun does not rotate the way a solid planet does, because it's a ball of plasma rather than rock. Different latitudes rotate at different speeds, a phenomenon called differential rotation. The sun's equator completes a full rotation in about 25 days. Its polar regions take closer to 35. This might sound like a minor technical curiosity, but it turns out to be one of the central engines driving almost everything else strange about the sun's behavior, because it takes the sun's initially orderly, simple magnetic field and slowly, relentlessly winds it up like an over-tightened spring, a process that, over years, builds toward the kind of magnetic violence that defines the sun's most dangerous behavior. To understand that violence, though, we first have to follow the sun's atmosphere further out, into a layer that shouldn't, by any ordinary logic, exist at all. The Corona paradox. Here is a fact that took physicists the better part of a century to fully believe, because it violates one of the most basic intuitions we carry about heat. The sun's outer atmosphere, called the corona, is hundreds of times hotter than the visible surface directly beneath it. The photosphere, the layer we normally think of as the sun's surface, sits at a temperature of roughly 5,500 degrees Celsius, blisteringly hot by any earthly standard. But modest as stellar temperatures go, move outward, away from that surface, into the wispy, extraordinarily faint outer atmosphere that becomes visible to the naked eye only during total solar eclipse. And instead of continuing to cool, as basic thermodynamics would suggest it should, the temperature suddenly and dramatically spikes to somewhere between 1 and 3 million degrees Celsius, in places even higher. Moving away from a heat source, the corona somehow gets hotter, not colder. It is roughly the equivalent of walking away from a bonfire and finding the air 10 meters away is 300 times hotter than the flames themselves. This is called the coronal heating problem, and it is, remarkably, still not fully solved. One of the longest-standing open questions in solar physics, still being actively investigated with some of the most sophisticated instruments humanity has ever built. Whatever mechanism is heating the corona has to be extraordinarily efficient and extraordinarily localized, concentrating enormous amounts of energy into the tenuous, wispy outer atmosphere, while somehow bypassing the much denser, cooler photosphere sitting directly below it. Two leading explanations currently compete for the answer, and it's entirely possible both are true simultaneously, working together. The first involves what are called nanoflares, a term coined by physicist Eugene Parker in 1988 to describe an idea that has only recently become directly testable. The sun's surface is threaded with countless tangled magnetic field lines, twisted and stressed by all that differential rotation and roiling convection underneath. Parker proposed that these tangled fields don't release their pent-up energy in occasional large, dramatic flares alone, but constantly, in a continuous blur of tiny magnetic snap-and-release events too small and too brief for most instruments to individually detect, each one a billionth the energy of a major solar flare, but happening so relentlessly, everywhere across the sun's surface, all the time, that their combined effect could be enough to superheat the entire corona. The second explanation involves waves, rather than tiny explosions, specifically Alfvén waves, a type of oscillation that travels alone. Magnetic field lines the way a wave travels down a plucked guitar string, carrying energy up from the turbulent surface into the corona, where it's converted into heat through various turbulent and resonant processes. Evidence for both mechanisms has been mounting, particularly since NASA's Parker Solar Probe, a spacecraft built with a heat shield capable of surviving temperature no previous mission had ever attempted to endure, began flying directly through the corona itself starting in 2021, becoming the first human-built object to touch a star. Its measurements have captured both tangled magnetic switchbacks in the solar wind, consistent with small-scale magnetic reconnection events, and wave-like turbulence consistent with the Alfvén wave heating picture, suggesting the true answer may involve both mechanisms working in concert, in ways still being untangled from the data. What makes the corona genuinely dangerous, rather than merely a beautiful scientific puzzle, is what it becomes once you follow it far enough out. The corona is so hot that the sun's own gravity, immense as it is, cannot hold on to all of it. A continuous stream of charged particles, mostly protons and electrons, escapes the corona entirely and flows outward through the entire solar system at speeds ranging from roughly 400 to 800 kilometers per second. This outflow is called the solar wind, and it is not a gentle breeze in any sense the word implies on Earth. It is a relentless, radiation-laced riviera of plasma, constantly buffeting every planet, comet, and spacecraft in the solar system, shaping the tails of comets, compressing and distorting planetary magnetic fields. And, on the rare and violent occasions, the sun decides to really lose its temper, threatening to overwhelm the delicate technological infrastructure of the one planet, with a civilization advanced enough to notice the sun's magnetic chaos. Everything genuinely dangerous about the sun, every flare, every eruption, every event capable of reaching across 93 million miles of empty space and disrupting a satellite or a power grid, traces back to one underlying cause: magnetism, angled and mismanaged on a scale that defies ordinary intuition. The sun's magnetic field starts out at the beginning of each roughly 11-year cycle, relatively simple, something closer to the tidy, symmetrical field of a bar magnet, running from one pole to the other in smooth, orderly arcs. But because the sun is not a rigid solid, and because different latitudes rotate at different speeds, thanks to differential rotation, that initially tidy field does not stay tidy for long. The equator, spinning faster than the poles, drags its portion of the magnetic field around with it, stretching and shearing the once smooth field lines into increasingly tight, twisted spirals. The way a rubber band wound relentlessly around a spinning axle grows tighter and tighter, storing more and more elastic energy with every turn. This winding process is called the solar dynamo. And it is, in essence, the sun's own version of an electrical generator, powered not by any external engine, but by the sheer scale of convecting plasma and differential rotation acting on the sun's own internal magnetic field, continuously regenerating and reorganizing it over the course of roughly 11 years. This winding process builds the field from its simple, orderly starting configuration into something almost unrecognizably tangled, concentrated into intense, localized ropes and loops that punch up through the photosphere as sunspot pairs, and eventually, having wound about as tight as it can go, the field reaches a kind of magnetic breaking point, flips its overall polarity entirely, north becoming south and south becoming north, and begins the whole tightening process over again in the opposite direction. This is why the full magnetic cycle of the sun is technically about 22 years, even though the sunspot cycle we usually talk about, based purely on counting spots without tracking polarity, appears to repeat roughly every 11. All that stored magnetic tension has to go somewhere eventually, and the process by which it's released is called magnetic reconnection, one of the most energetic phenomena known to physics. When two oppositely oriented magnetic field lines are forced close enough together, they can suddenly snap and reconnect into a new, lower energy configuration, releasing the difference in energy almost instantaneously, in the form of intense heat, high-speed particle jets, and bursts of radiation across the entire electromagnetic spectrum. And it is, in a rough sense, the magnetic equivalent of an overstretched rubber band finally snapping, except that the rubber band in question can be tens of thousands of kilometers long, and the energy released in a single major reconnection event can exceed, by some estimates, the combined output of 1 billion nuclear bombs unleashed in a matter of minutes. The sun's magnetic behavior doesn't just drive short-term events like flares. It appears to modulate the sun's activity over far longer timescales as well, in ways that remain only partially understood. Between roughly 1645 and 1715, astronomers recorded a period during which sunspots became extraordinarily rare, sometimes vanish, being from the sun's face for years at a stretch. This period, now called the Maunder Minimum, coincided closely with an unusually cold stretch of European and North American climate history, sometimes referred to as the Little Ice Age. Though the precise causal relationship between reduced solar magnetic activity and regional cooling remains an area of active, carefully hedged research rather than settled fact, since the Little Ice Age had multiple contributing causes, including volcanic activity, and the size of the solar contribution is still debated among climate scientists. What the Maunder Minimum does establish clearly is that the sun's furious magnetic activity is not a fixed, unchanging constant, even on human timescales. It waxes and wanes across decades and centuries in patterns we can document historically, but still cannot fully predict or explain. All of this tangled, cyclical, occasionally catastrophic magnetism sets the stage for the sun's most dramatic, and for a civilization built on electronics, most genuinely threatening behavior. The moment all that carefully wound up tension finally, violently, lets go. When the sun screams, a solar flare is, at its core, a magnetic reconnection event on a scale that can be seen and measured from 93 million miles away. When a sufficiently large, sufficiently twisted knot of magnetic field lines above a sunspot group finally snaps and reconnects, the released energy accelerates charged particles to extraordinary speeds and heats the surrounding plasma to tens of millions of degrees, in some cases briefly hotter than the sun's own core. The result is a sudden, intense burst of radiation across virtually the entire electromagnetic spectrum. Radio waves, visible light, ultraviolet rays, and gamma rays, all released essentially simultaneously, all traveling at the speed of light, reaching Earth in about 8 minutes flat, with no advance warning possible, because nothing can outrun the light announcing the event. Solar flares are classified by their peak X-ray brightness into a letter scale: A, B, C, M, and X, each category roughly 10 times more energetic than the one before it, with a numerical suffix indicating relative strength within that category. B-class flare is a minor, almost routine event. An X-class flare is a genuinely major event, capable of triggering radio blackouts on the sunlit side of Earth within minutes, and, depending on strength and direction, posing real risk to satellites, high-altitude aircraft, and astronauts outside adequate shielding. The scale is technically open-ended at the top. An X9 flare is 9 times more powerful than an X1, and the most powerful flare ever directly measured by modern instruments, in November 2003, actually overwhelmed the sensor recording it. Based on the data available before saturation, estimates place it somewhere around X28, though the true peak strength remains genuinely uncertain, precisely because the event was so powerful, it broke the equipment designed to measure it. Flares alone, however dramatic, are not usually what poses the greatest practical threat to Earth's technology. That distinction belongs to a related but distinct phenomenon called a coronal mass ejection, or CME, an event in which the sun doesn't just release a burst of radiation, but hurls an enormous billion-ton bubble of magnetized plasma directly outward into space, sometimes at speeds exceeding 2,000 kilometers per second. Where the electromagnetic radiation from a flare reaches Earth in 8 minutes, a CME is physical material, and physical material is bound by the ordinary rules of momentum travel time. A fast CME aimed directly at Earth typically takes somewhere between 15 and 18 hours to arrive, though slower ones can take several days. giving space weather forecasters a genuine, if uncomfortably narrow, window to issue warnings. When a CME's leading magnetic field slams into Earth's own protective magnetosphere, the interaction can trigger what's called a geomagnetic storm, a temporary but sometimes dramatic disturbance of Earth's magnetic field, driven by the sudden compression and reconnection happening at the boundary, where the incoming solar plasma meets our planet's own magnetic shield. The most immediately visible consequence is the aurora, the northern and southern lights, which during a strong storm can be pushed from their usual polar habitats down latitudes that almost never see them, painting skies over places like the American Midwest or Southern Europe in shimmering green and crimson light. Auroras are the visible, beautiful signature of an interaction that, at greater intensity, can also induce powerful, unwanted electrical currents in any sufficiently long conductor on Earth's surface, undersea cables, pipelines, and, most consequentially of all, the high-voltage power grid that keeps modern civilization running. It is worth being precise about the physical mechanism here, because it's genuinely counterintuitive. A geomagnetic storm doesn't damage electronics by bathing them in dangerous radiation the way, say, a nuclear event might. It works through electromagnetic induction, the same basic physics behind an electrical generator. A rapidly fluctuating magnetic field, sweeping across a long conductor, induces an electrical current in that conductor, whether or not anyone wants one there. The longer the conductor, the larger the induced current, which is precisely why continent-spanning power transmission lines, pipelines, and undersea communication cables are so vulnerable, and why a compact, well-shielded device sitting in your pocket is comparatively safe. That isn't the sun reaching down and frying our electronics directly. It's the sun accidentally turning our own infrastructure into an enormous, unintended electromagnet, pumping current into systems never designed to carry it. A Carrington event. On the 1st of September, 1859, an English astronomer named Richard Carrington was doing something he did most clear mornings, sketching sunspots, projecting an image of the sun's disk through his telescope onto a screen to protect his eye, carefully tracing the shapes of a particularly large and complex sunspot group he had been tracking for days. At around 11:18 in the morning, without warning, two brilliant points of white light suddenly blazed out from within the sunspot group, intensifying for several minutes before fading. Carrington had just become one of the first people in recorded history to witness and document a solar flare, though neither he nor anyone else alive at the time had any framework for understanding what he'd actually seen. What Carrington couldn't have known, watching those 2 points of light fade back into the ordinary glare of the sunspots, was that his telescope had just captured the opening act of what remains, to this day, the most powerful geomagnetic storm in recorded history. Roughly 17 hours later, startlingly fast for a CME, suggesting the plasma cloud had been hurled toward Earth at extraordinary speed, likely because an earlier, small eruption had already cleared a relatively unobstructed path through the solar wind for the second, larger one to follow. The associated coronal mass ejection slammed into Earth's magnetosphere. The effects, for a 19th century world with only the barest scaffolding of electrical technology, were still extraordinary. Auroras, normally confined to polar latitudes, blazed across the sky as far south as Cuba, Hawaii, and Colombia, bright enough, according to numerous contemporary accounts, that people in the northeastern United States reported being able to read a newspaper by their light in the middle of the night, and gold miners in the Rocky Mountains reportedly woke and began preparing breakfast mistaking the auroral glow for the approach of dawn. The one significant piece of long-distance electrical infrastructure that existed at the time, the telegraph network, strung across 1,000 miles of North America and Europe, bore the brunt of the storm's induced currents. Telegraph operators reported sparks leaping from their equipment, some receiving mild electric shocks through their instruments, and paper telegraph tape catching fire in a handful of documented cases. Remarkably, several operators discovered they could disconnect their batteries entirely and continue sending messages for a time, using only the current being induced directly into the lines by the storm itself, powered, briefly, by the sun. The Carrington event caused real disruption and real damage in 1859, but the world it disrupted was, by modern standards, almost laughably simple. A scattering of telegraph wires representing essentially the entire long-distance electrical grid then in existence. Genuinely unsettling exercise, the one that occupies space weather researchers and infrastructure planners today, is asking what a storm of that same magnitude would do to a world that now runs almost its entire economy, government, and daily life through interconnected electrical and electronic systems vastly more extensive, more interdependent, and more sensitive than a few strands of telegraph cable ever were. We don't have to rely purely on hypothetical modeling to guess. In March 1989, a considerably smaller geomagnetic storm, still powerful, but a fraction of Carrington's estimated intensity, induced enough current in Hydro-Quebec's power grid to trip protective relays and collapse the entire system within about 90 seconds, plunging 6 million people in Quebec, Canada, into darkness for approximately 9 hours in the middle of a Canadian winter. Transformers as far away as New Jersey sustained physical damage from the same storm. It was a sobering, concrete demonstration on a fraction of Carrington's scale of exactly the vulnerability space weather researchers had been warning about. And it was, as the next chapter of this story makes clear, far from the closest call the modern world has actually faced. The near miss of 2012. On the 23rd of July, 2012, the sun produced a coronal mass ejection that solar physicists studying it afterward would come to regard as comparable in scale and speed to the Carrington event of 1859. Quite possibly, it's equal or close to it. The eruption tore outward from the sun at a velocity later estimated around 3,000 kilometers per second, among the fastest CME speeds ever directly measured, capable, had it been aimed differently, of crossing the roughly 93 million miles between the sun and Earth in under 20 hours. It missed us, not by a wide margin in cosmic terms, but by a margin that, on reflection, should give anyone pause. The eruption occurred on a part of the sun that happened, at that particular moment, to be facing away from Earth, along almost exactly the same region of the solar surface Earth itself had occupied. From the sun's point of view, just 9 days earlier, had the eruption occurred a little over a week sooner in the sun's rotation, the CME would have been heading directly for us. The event wasn't entirely unwitnessed, even though it missed Earth. NASA's Styroa spacecraft, positioned at a different vantage point in the inner solar system, specifically to observe the sun from angles unavailable to Earth-based instruments, happened to be almost perfectly positioned to capture the eruption in exceptional detail, giving researchers an unusually complete dataset to reconstruct exactly how powerful the event had been and precisely how close a call humanity had actually experienced. A subsequent study, led by physicist Daniel Baker and colleagues, drawing on that data, concluded that had the July 2012 CME struck Earth directly, the resulting geomagnetic storm would very likely have rivaled or exceeded the Carrington event in intensity. And unlike 1859, it would have been striking a civilization utterly dependent on the electrical grid and electronics. It would have threatened. Estimates of the potential economic damage from a direct Carrington-class strike on modern infrastructure vary considerably depending on the assumptions built into each model, reflecting real, unresolved scientific and engineering uncertainty about exactly how vulnerable different components of the grid actually are. But even the more conservative estimates published in the scientific and engineering literature place the potential cost in the hundreds of billions to low trillions of dollars in the United States alone, with recovery time for the most severely affected regions potentially stretching from months to, in worst-case transformer failure scenarios, over a year, given how few spare high-voltage transformers exist in reserve worldwide, and how long custom-built replacements typically take to manufacture and ship. These figures carry meaningful uncertainty and shouldn't be treated as a precise forecast. Legitimate researchers in this field disagree substantially on the detail, but the consistent conclusion across multiple independent studies is that the scenario is neither implausible nor free of serious consequence. What makes the 2012 near miss so unsettling, in retrospect, isn't just its raw power. It's the reminder that events of this scale are not once in a millennium curiosities safely confined to the history books. Solar physicists studying long-term records now estimate that Carrington-class or larger events strike the general vicinity of Earth's orbit with rough order of magnitude frequency on the order of once every century or two, though pinning down a precise recurrence rate remains genuinely difficult given how short and incomplete our detailed observational record actually is. Reliable, continuous solar monitoring only stretches back a comparatively short span of decades. The 2012 event didn't reveal a freak anomaly. It revealed that we came within 9 days, on an essentially random roll of the sun's own rotation, of finding out exactly how prepared or unprepared 21st century civilization actually is. What a direct hit world actually do. It's worth walking through carefully and without exaggeration what space weather researchers and infrastructure engineers actually believe would happen in the hours, days, and months following a Carrington-class geomagnetic storm striking a modern, technologically dependent region head-on, not as speculative fiction, but as a synthesis of the genuine, published risk assessments produced by agencies and researchers who study this professionally. The first and most immediate effect would unfold in the ionosphere, the electrically charged upper layer of Earth's atmosphere that global positioning systems and much long-range radio communication depend on. Intense geomagnetic disturbance distorts and disrupts this layer, degrading or entirely blacking out GPS accuracy and high-frequency radio communication across the sunlit hemisphere for a period ranging from hours to, in a severe event, potentially days, given how deeply GPS timing signals, not just positioning, but the precise timing signals GPS satellites broadcast, have been quietly woven into systems far beyond simple navigation, including financial transaction timestamping and the synchronization of power grid operations themselves. This disruption alone would ripple outward into sectors that have little obvious connection to satellite navigation on the surface. Satellites themselves face direct risk from the associated burst of energetic particles, which can degrade solar panels, damage sensitive electronics through a phenomenon called single event upset, where a high-energy particle flips a bit in a computer memory system, and in severe cases cause permanent component failure. Low Earth orbit satellites face an additional, subtler danger. A strong geomagnetic storm heats and expands Earth's upper atmosphere, increasing atmospheric drag on satellites in low orbits and potentially pulling some out of their intended orbital paths faster than their onboard fuel reserves can compensate for. A real, documented effect seen at smaller scale during ordinary geomagnetic storms that becomes considerably more serious during an extreme event. With many thousands of satellites now in low orbit, a substantial fraction of modern global communication, imaging, and weather monitoring infrastructure would be exposed simultaneously. But the most consequential risk, by most professional assessments, remains the high-voltage power transmission grid. For the same fundamental reason, it caused the Quebec blackout of 1989 on a much smaller scale. Extremely long conductors are extremely efficient at having current induced in them by a fluctuating magnetic field, and modern power grids are built from exactly that. Thousands of kilometers of high-voltage transmission lines connecting large regional networks together. The induced currents involved aren't ordinary alternating current. They're geomagnetically induced currents, closer to direct current, which large power transformers are not designed to handle. Feed enough of this unwanted current into a transformer, and it can overheat, sometimes to the point of permanent physical damage, in a matter of minutes. Herein lies the specific, well-documented worst-case scenario that concerns infrastructure planners most. Unlike most large industrial equipment, the largest high-voltage transformers used in transmission grids are not off-the-shelf items. They are typically custom-built to the specifications of a particular substation, weigh hundreds of tons, are manufactured by a relatively small number of facilities worldwide, and historically have required anywhere from several months to well over a year to manufacture and deliver under normal circumstances. A timeline that assumes ordinary, non-emergency demand on the small number of factories capable of producing them. A severe geomagnetic storm capable of damaging dozens or hundreds of these transformers simultaneously across an affected region, as some modeling scenarios suggest is plausible for a Carrington-class event striking heavily populated, high-latitude areas, could genuinely outstrip global manufacturing capacity to replace them quickly, extending outages in the worst affected areas from the hours or days typical of an ordinary storm-related blackout into a genuinely prolonged, months to potentially longer recovery, with all the cascading consequences for water treatment, food distribution, healthcare, banking, that an extended large-scale power outage implies. It bears repeating clearly. This is a worst-case scenario built from published, peer-reviewed risk assessments, not a certain or even necessarily probable outcome of the next major solar storm. Considerable uncertainty remains in the scientific and engineering literature about exactly how many transformers would actually fail, how vulnerable specific regional grids are given their particular geology and design, and how effective existing and newly developed mitigation measures, such as installing current blocking devices on the most vulnerable transformers, and issuing earlier storm warnings to allow grid operators to take protective action, would prove to be in an actual event. Space weather agencies around the world, along with grid operators, have taken this risk seriously enough in recent years to build out considerably more sophisticated monitoring and early warning systems than existed even a decade ago. The point of walking through this scenario isn't to declare it inevitable. It's to make clear why a star most of us picture as a source of gentle, dependable warmth is treated by the people whose job is to actually plan for it as a genuine, active item on the list of civilizational risks worth serious, ongoing attention. why we can't predict it. Given how much is riding on the sun's behavior, it would be reassuring to say that modern science can reliably predict when the next major flare or CME will occur with enough advance warning to prepare thoroughly. It largely can't, and understanding exactly why reveals something important about the underlying nature of the phenomenon. The 11-year sunspot cycle itself, the broad rhythm of rising and falling solar activity, is reasonably well understood in its general shape, even if the underlying dynamo mechanism driving it isn't fully solved in every detail. But predicting the precise strength of an upcoming cycle, or exactly when it will peak, has proven stubbornly difficult, and forecasts issued by different research groups using different modeling approaches have, on multiple occasions in recent decades, disagreed substantially with each other and with what the sun actually went on to do. The current solar cycle, numbered Cycle 25 by the convention astronomers have used since systematic sunspot counting began in the mid-18th century, was forecast by an official panel to be relatively weak, comparable to or slightly stronger than the notably quiet cycle before it, and instead arrived considerably more active than that forecast anticipated, a reminder that even the broad multi-year rhythm of solar activity resists confident prediction. Predicting an individual flare or CME days or weeks in advance is, at present, simply not possible with any reliability. Solar physicists can identify sunspot regions that look magnetically complex and therefore statistically more likely to produce a major flare in the coming days. A genuinely useful, actively used forecasting tool, but more likely is a long way from will definitely happen at this specific time, and plenty of magnetically simple-looking regions have produced unexpected major eruptions, while plenty of complex, closely watched regions have quietly decayed without incident. The underlying physics helps explain why. Magnetic reconnection, the mechanism actually triggering a flare, depends on the precise, small-scale geometry of tangled field lines reaching a critical, unstable configuration, a process with genuine chaotic sensitivity, where very small differences in the exact arrangement of the magnetic field can determine whether a region erupts explosively or simply relaxes back toward a calmer state. It shares something in common, structurally, with the reasons weather forecasting on Earth remains reliable only a matter of days out, despite our comparatively enormous investment in atmospheric monitoring. The underlying system is genuinely chaotic, sensitive to initial conditions too fine-grained for any monitoring network to capture completely. Once a flare or CME does occur, the situation for near-term prediction improves considerably, but the warning window remains uncomfortably tight. Flare-associated radiation reaches Earth at the speed of light, offering essentially zero advance warning. By the time any instrument detects the flare, its radiation has already arrived. CMEs, being physical matter rather than light, do offer a genuine warning window, typically somewhere between roughly 15 hours and several days depending on speed and spacecraft position between the Sun and Earth. Most critically, a satellite called DSCOVA, stationed at a gravitationally stable point roughly 1 million miles from Earth toward the Sun, provide a final, crucial confirmation of a CME's speed, density, and, most importantly, its magnetic orientation, roughly 50 to 60 minutes before it actually arrives. That magnetic orientation turns out to matter enormously. A CME whose magnetic field happens to align in a particular way relative to Earth's own field can interact far more violently and effectively than an otherwise identical CME oriented differently. And that crucial detail, more than almost anything else, generally cannot be determined with confidence until the CME is already bearing down, leaving grid operators and satellite controllers a genuinely narrow window to take whatever protective action they can, all of which points toward an uncomfortable but scientifically honest conclusion. The sun's most dangerous behavior sits at the intersection of two things human forecasting is fundamentally bad at: a chaotic underlying process resistant to precise prediction, and a warning window measured, in the worst cases, in minutes rather than days. Improving that picture, building better models of the sun's interior, launching more comprehensive monitoring spacecraft, refining our understanding of exactly which magnetic configurations reliably precede major eruptions, remains one of the active funded priorities of solar physics, precisely because the stakes of getting wrong keep growing as civilization becomes more electronically interconnected with each passing year. The sun's hidden interior. Everything described so far. The core, the radiative zone photons spend millennia crossing. The convective churn that produces surface granulation sits behind an opaque wall no telescope of any kind, operating at any wavelength, can see direct lie through. The sun is not remotely transparent. Visible light, X-rays, and every other form of electromagnetic radiation are absorbed and scattered long before they could carry information from the interior back out to an observer. Most of the history of solar science, the sun's inner structure was inferred entirely indirectly, built from theoretical models constrained by whatever could be measured at the surface, with no way to check those models directly against the hidden reality producing them. That changed with the development of a field called helioseismology, and the underlying idea, once you hear it, has an almost poetic elegance. The sun rings constantly, like an enormous, extraordinarily complex bell, and by carefully listening to exactly how it rings, physicists can reconstruct a surprisingly detailed picture of what's happening inside, layer by layer, all the way down toward the core. Ringing in question consists of sound waves, genuine acoustic pressure waves, not so different in basic physics from the sound waves carrying a human voice through air, generated continuously by the violent, turbulent convection roiling just beneath the visible surface. These waves propagate down into the sun's interior, refract, and reflect off boundaries between different internal layers according to precise physical laws, and eventually return to the surface, where they cause the entire visible disk of the sun to oscillate, expanding and contracting in complex, overlapping patterns, typically with periods of around 5 minutes. These oscillations are far too subtle to notice with the naked eye, but sensitive instruments, watching the sun continuously, can detect the resulting tiny, rhythmic shifts in the wavelength of light coming from different points across the solar disk, revealing the underlying pattern of sound waves washing through the star's interior. By carefully analyzing millions of these overlapping oscillation patterns, a technique with real conceptual kinship to how a medical ultrasound reconstructs a picture of internal soft tissue from reflected sound waves, or how seismologists reconstruct Earth's internal layered structure from the way earthquake waves travel through it. Solar physicists have been able to map the sun's internal structure with genuine precision, confirming the boundary between the radiative zone and the convective zone lies at roughly 70% of the way out from the core to the surface, measuring the precise and surprisingly complicated pattern of the sun's internal differential rotation layer by layer, and even, in more recent and technically demanding work, detecting hints of activity in the deep core itself, far beneath any layer directly observable by conventional astronomy. One of heliosmology's most striking discoveries concerns the boundary layer between the Sun's inner radiative zone, where energy moves outward primarily via a slow photon random walk, and the outer convective zone, where energy instead moves via bulk churning motion of plasma, not unlike water boiling in a pot. This transition region, called the tachocline, turns out to be a site of intense internal shear, where the different rotation rates of the radiative zone below and the convective zone above grind against each other continuously. And a growing body of research suggests the tachocline may play a central, though still not fully worked out, role in generating and organizing the Sun's overall magnetic field, potentially serving as the primary engine of the solar dynamo process described earlier. It is, in other words, a hidden layer, invisible to direct observation, discovered only through the patient analysis of the Sun's own acoustic ringing, that may sit at the very root of everything from sunspots to the flares and coronal mass ejections capable of reaching Earth and disrupting a modern power grid. A star like no other we've found. Every threat described so far in this documentary, the flares, the coronal mass ejections, the Carrington scale storms, falls within a range of solar behavior humanity has directly observed, documented, and to some degree, learned to plan around. But a genuinely uncomfortable question has emerged in solar physics over roughly the last decade and a half, driven largely by data from an entirely different kind of instrument, originally built for an entirely different purpose. Could the Sun ever produce something dramatically, catastrophically more powerful than anything in its recorded history? NASA's Kepler Space Telescope, launched in 2009, was designed primarily to search for planets orbiting distant stars by watching for the tiny, telltale dips in brightness that occur when a planet passes directly in front of its host star. In the process of monitoring the brightness of well over 100,000 stars continuously, and with extraordinary precision over several years, Kepler also happened to record something its designers hadn't specifically set out to find. Sudden, dramatic spikes in brightness on a substantial number of Sun-like stars, stars of similar mass, temperature, and age to our own Sun, consistent with flares vastly, almost unimaginably more powerful than anything the Sun has produced within recorded human history. Researchers led by Hiroyuki Maehara published an influential 2012 analysis identifying these events as superflares, with energies in some cases thousands times greater than the most powerful flare the Sun has ever been observed to produce. Genuinely uncomfortable question this raised, and one that solar and stellar physicists have been actively debating and researching ever since, is whether these superflare-producing stars represent some special, unusual category fundamentally different from our own Sun, or whether they represent a category our own Sun could, at least in principle, occasionally belong to as well, meaning a Carrington-class event, dramatic as it sounds, might not represent anywhere close to the Sun's true theoretical upper limit of destructive potential. Early analyses suggested many of the most extreme superflare stars might be unusual in ways that could explain their behavior, potentially closer binary companions, or younger, more rapidly rotating, more magnetically active stars than our comparatively calm, middle-aged Sun. But more recent research, including a widely discussed 2019 study led by Yuta Notsu, using refined stellar classification data, found that a meaningful subset of the superflare-producing stars appeared, by their measured rotation rates, ages, and other properties, to be genuinely comparable to the Sun, raising the statistically grounded, though still far from certain, possibility that superflares many times more powerful than anything in recorded solar history might occur on Sun-like stars. including potentially our own, albeit apparently at a much lower frequency than on the more active, unusual stars in Kepler's dataset. It would be scientifically irresponsible to overstate where this research currently stands. No superflare has ever been observed on our actual sun in the entirety of recorded human history, going back thousands of years across multiple ancient civilizations that documented unusual celestial events, and some researchers in the field remain genuinely skeptical that the sun is truly capable of superflare scale events given what's understood about its current age, rotation rate, and magnetic behavior. What the research does establish, at minimum, is that the question is a live, actively contested one within the scientific literature, rather than a settled matter either way, and that some of the same statistical methods used to identify these superflares on other stars have separately been applied to searching Earth's own geological and historical record for direct evidence of past extreme solar events, including analysis of rare radioactive isotopes preserved in tree rings and ice cores, which has identified at least a couple of high-date events, sometimes called Miyake events, after the researcher who first identified the signature, that some scientists argue may represent solar particle storms considerably more intense than the Carrington event, embedded in Earth's own physical record going back over 1,000 years, though the interpretation of these isotope signals, whether they represent extreme solar events specifically, as opposed to some other astrophysical cause, also remains an area of genuine ongoing scientific debate rather than settled consensus. The long death. Everything discussed to this point concerns the sun as it exists today, in what astronomers call its main sequence phase. The long, comparatively stable middle stretch of a star's life, during which it steadily fuses hydrogen into helium in its core, maintaining that careful hydrostatic balance between gravity and outward pressure that has held, essentially unbroken, for 4.5 billion years. But main sequence stability, however durable it seems set against a single human lifetime, is not a permanent condition. It is a phase with a beginning, a middle, and eventually an end. And the sun, roughly halfway through its main sequence lifespan, has already used up close to half of the hydrogen fuel available in its core in approximately 5 billion years, a span of time so vast it resists genuine intuition, roughly equal to the entire age of the sun up to this point, repeated once more. The sun's core will have exhausted its hydrogen supply, having gradually converted the overwhelming majority of it into helium. And at that point, without sufficient hydrogen fusion in the core to maintain the outward pressure that has held gravity in check for billions of years, the core will begin to contract under its own weight, heating as it does so. That contraction won't simply extinguish the star. Instead, the intensifying heat around the shrinking, helium-rich core will ignite hydrogen fusion in shells surrounding it, in a layer that had previously been too cool for fusion to occur. The shell-burning phase will dramatically increase the sun's energy output, and the star's outer layers, responding to that surge, will expand outward on a scale difficult to overstate, transforming the sun from the relatively compact star we know today into a red giant, potentially swelling to somewhere between 100 and 200 times its current diameter. Consequences for the inner solar system are almost impossible to view as anything other than catastrophic, though the precise fate of individual planets remains a object of genuine, careful scientific debate rather than settled certainty. Mercury, the innermost planet, will almost certainly be engulfed entirely its orbit lying well within the red giant sun's projected expanded radius under most current models. Venus faces a similarly near certain fate. Earth's situation sits closer to the genuine edge of current models' uncertainty. Some calculations suggest Earth's orbit will have expanded outward somewhat by that point, as the sun sheds mass through increasingly powerful stellar winds during the red giant phase, potentially loosening gravity's grip enough to let Earth's orbit drift to a slightly safer distance, while other models, accounting for tidal drag between the swollen outer atmosphere of the expanding sun and Earth's orbit, suggest that drag could pull Earth's orbit inward, even as the sun's mass loss pushes it outward, with the modeled net outcome landing close enough to the boundary between survival and engulfment that current science genuinely cannot say with confidence which effect wins. What is not remotely in serious scientific doubt, regardless of whether Earth is technically engulfed or merely grazed by the expanding outer atmosphere of a red giant sun, is that the planet will be rendered completely, catastrophically uninhabitable long before that final expansion phase even arrives. The sun's total energy output is already, gradually, increasing over time, as billions of years of steady core fusion slowly change its internal structure and chemistry even during the ordinary main sequence phase. A slow brightening on a timescale of hundreds of millions to a few billion years that most climate and planetary scientists studying long-term Earth habitability now consider likely to render Earth's surface too hot to sustain liquid water and complex life somewhere in the range of 1 to 2 billion years from now, an event that will arrive dramatically sooner, in cosmic terms, than the red giant expansion itself, which remains billions of years further out still. Eventually, following the red giant phase, the sun will exhaust even its shell fusion fuel, shed its outer layers entirely in a relatively gentle stellar wind, rather than the violent supernova explosion reserved for far more massive stars, forming a brief, glowing shell of expelled gas astronomers call a planetary nebula, and leaving behind, at its center, the exposed, superdense, no longer fusing core, a white dwarf, roughly the size of Earth, but containing something close to the sun's entire remaining mass, slowly cooling over trillions of years, far longer than the current age of the universe, gradually fading from view without ever entirely going dark. It is, by the standards of stellar death across the universe, an almost gentle ending. No explosive violence, no neutron star, no black hole. The quiet, patient conclusion appropriate to a star that spent its entire working life following exactly the same kind of careful, self-regulating balance that made it capable of nurturing a solar system and, briefly, a civilization in the first place. The sun that made US set everything in this documentary side by side. The violent magnetic tangling, the flares capable of darkening cities, the ever-present possibility of a Carrington-class or even super-flare-class event, the eventual certainty of a red giant expansion will end life on Earth entirely, and a genuine paradox emerges, one worth sitting with, as we bring this story to a close. The same unpredictable, occasionally furious, ultimately mortal star is also, without any real competition, the single most important reason complex life exists on Earth at all. Ability, it turns out, is a relative term, and by the standards that actually matter for the long, patient chemistry of life, the sun has been remarkably, almost impressively stable across the timescale that counts. Compare it to many of the smaller, cooler, far more numerous red dwarf stars scattered across the galaxy. Stars that, despite burning at much lower overall temperatures, are frequently dramatically more magnetically volatile than the Sun relative to their size, producing flares proportionally powerful enough to regularly strip away the atmospheres of any close-orbiting planet, a serious complication for the search for habitable worlds around the very stars that are statistically most common in our galaxy. Measured against that broader stellar population, the Sun's roughly 11-year cycle of waxing and waning activity, punctuated by occasional, genuinely dangerous, but ultimately survivable outbursts, represents something closer to the calm end of the spectrum. Turbulent enough to be worth taking seriously, calm enough, across 4.5 billion years, to have allowed liquid water, and eventually life, and eventually a species capable of building telescopes and writing documentaries about the star responsible, to emerge and persist. It's worth returning one final time to the almost absurd inefficiency described earlier in this story. The fact that the Sun's core generates heat, gram per gram, barely faster than a compost heap. That very inefficiency, so easy to describe as almost comical, is arguably one of the central reasons life on Earth had time to happen at all. Our fusing its hydrogen fuel more aggressively, more quickly, would burn through its main sequence lifespan far faster, potentially in a matter of only millions of years rather than billions, leaving nowhere near enough time for the slow, patient chemistry of abiogenesis and evolution to produce anything as complex as a single-celled organism, let alone a species capable of building a civilization around it. The Sun's almost sluggish, deeply inefficient rate of fusion, so slow that any individual proton in its core waits, on average, roughly 10 billion years for its turn to fuse, turns out to be precisely the pace that bought Earth's biosphere the roughly 4 billion years it needed to go from simple chemistry to complex, self-aware life. Every atom of carbon in your body, every atom of oxygen you just breathed, every trace of calcium in your bones and iron in your blood was forged inside the nuclear furnace of some earlier star that lived, fused heavier and heavier elements, and eventually died. Long before the Sun and the rest of the solar system condensed out of the resulting enriched cloud of gas and dust roughly 4.5 billion years ago. In a very real, physically literal sense, you are made of stardust from stars that came before the Sun, warmed and given the specific, sustained energy needed to organize into something as intricate as a living cell, and eventually a thinking mind by the specific star that happened to end up at the center of this particular solar system. That is the genuine, unresolved tension sitting at the heart of everything this documentary has described. The Sun is not the gentle, dependable, unchanging presence popular imagination assigns it. It is a churning, magnetically volatile plasma furnace capable of unleashing, without meaningful advance warning, more energy in a matter of minutes than human civilization has generated across its entire recorded history. A star we remain, in a very real technological sense, at the mercy of, watching nerve fly with an ever-improving, but still fundamentally limited set of instruments, hoping the next major eruption points somewhere other than directly at us. And it is, simultaneously, precisely because of its particular balance of violence and restraint, precisely because of its almost sluggish rate of fuse, ion, and its comparatively calm place among the wider population of stars. The single specific reason any of this, the Earth, the biosphere, the species capable of asking these questions in the first place, exists to be threatened at all. The discovery of what the Sun is made of for most of the 19th century, one question about the Sun seemed permanently, definitionally out of reach. What is it actually made of? The sun sits some 93 million miles away, far too hot and far too bright to ever visit, sample, or bring a fragment of back to a laboratory bench. The French philosopher Auguste Comte, writing in 1835, chose the chemical composition of the stars as his go-to example of a question science would never be able to answer. A piece of knowledge, he argued, permanently, and by its very nature, beyond the reach of any conceivable observation. Within a few decades, he would be proven completely, spectacularly wrong. The tool that overturned Comte's confident prediction was spectroscopy, the careful study of the specific wavelengths of light an object emits or absorbs. Early in the century, the German optician Joseph von Fraunhofer, testing the quality of his own glass lenses and prisms, noticed something odd when he passed sunlight through a prism and examined the resulting rainbow of colors closely. Rather than a perfectly smooth, continuous spectrum, the rainbow was interrupted by hundreds of thin, dark, vertical lines at very specific, repeatable positions. Fraunhofer meticulously catalogued nearly 600 of these mysterious dark lines without being able to explain what caused them, and they came to bear his name, Fraunhofer lines, a puzzle sitting quietly at the heart of physics for decades. The explanation arrived in the 1850s and 1860s through the work of the German physicist Gustav Kirchhoff and the chemist Robert Bunsen, who discovered that every chemical element, when heated to incandescence, emits light only at a specific, unique set of wavelengths, a kind of optical fingerprint, different for every element on the periodic table, and reliably reproducible under laboratory conditions on Earth. Crucially, they also showed that a cooler gas, given the chance to absorb light passing through it, would absorb light at those exact same characteristic wavelengths rather than emitting it, carving thin dark lines out of an otherwise continuous, brighter spectrum passing through or behind it. Fraunhofer's mysterious dark lines suddenly made complete sense. They were the absorption fingerprints of specific chemical elements present in the cooler outer layers of the sun's atmosphere, each one selectively swallowing its own particular wavelengths of light on its way out from the blazing interior. For the first time in human history, it became possible to determine, with genuine scientific confidence, exactly which chemical elements existed in an object no human being could ever physically touch. Technique's most celebrated triumph followed within a decade, during a total solar eclipse in 1868, when the sun's normally invisible outer atmosphere, the corona and the layer just beneath it, became observable to the naked eye. French astronomer Pierre Janssen and, independently, English astronomer Norman Lockyer both examined the light streaming from the sun's edge using spectroscopes and found a bright yellow spectral line that matched no known element on Earth's periodic table. Lockyer proposed, correctly as it would turn out, that this represented an entirely new element, one that existed on the sun, but had not yet been found or identified anywhere on Earth. He named it helium, after Helios, the Greek personification of the sun, making it the only element in the periodic table discovered somewhere other than Earth before it was ever found here. It would be another 27 years before the Scottish chemist William Ramsay finally isolated a small sample of the same gas from a uranium-bearing mine in a laboratory on Earth, confirming Lockyer's identification and closing one of the more remarkable detective stories in the history of science. Modern spectroscopy, built on exactly the same underlying Fraunhofer line principle, but refined by more than a century and a half of technological advancement, now allows astronomers to determine the sun's composition with extraordinary precision. Roughly 3/4 of the sun's mass is hydrogen, the fuel for the fusion reaction described earlier in this story, and almost all the remainder is helium, the ash of billions of years of that same fusion process, steadily accumulating in the sun's core. Every other element on the periodic table combined, the carbon, oxygen, iron, silicon, and everything else, makes up less than 2% of the sun's total mass, present as trace residue inherited from the earlier generations of stars whose deaths, billions of years before the sun was born, seeded the cloud of gas and dust from which our entire solar system eventually condensed. The heliosphere, the sun's bubble around all of the solar wind, introduced earlier in this story as the continuous stream of charged particles escaping the sun's superheated corona, doesn't simply dissipate once it leaves the immediate vicinity of the sun. It keeps traveling outward in every direction, sweeping past Mercury, Venus, Earth, and every other planet in the solar system, all the way out past the orbit of Pluto and well beyond, carrying the sun's magnetic field embedded within it, stretching across a volume of space vastly larger than the orbits of all 8 planets combined, until it finally runs out of momentum and pressure, meeting resistance from the thin, diffuse gas and cosmic radiation that fills the space between stars. This entire enormous bubble, inflated by the sun and its magnetic field, is called the heliosphere. And every planet in the solar system, Earth very much included, it's well inside it. The heliosphere is not a passive, empty region. It functions, in a very real and physically measurable sense, as a protective shield, deflecting a substantial portion of the galactic cosmic rays that would otherwise reach the inner solar system unimpeded. These cosmic rays are extraordinarily high-energy particles, accelerated to a significant fraction of the speed of light by distant, ancient supernova explosions and other violent astrophysical events scattered across the galaxy, and they pose genuine risks to sensitive electronics and unshielded biological tissue alike. The heliosphere's outward-pushing solar wind and embedded magnetic field make it considerably harder for these particles to penetrate into the inner solar system, and by extension, harder for them to reach Earth's own atmosphere and surface, a layer of protection sitting outside and complementary to the more familiar protection provided by Earth's own planetary magnetic field. The boundary of this vast bubble, the region where the outward pressure of the solar wind finally weakens enough to be overcome by the surrounding pressure of interstellar gas and magnetic fields, is called a heliopause, and it sits, remarkably, more than 100 times farther from the sun than Earth does. For decades, this boundary existed only as a theoretical prediction, calculated from models of solar wind pressure and estimates of the interstellar medium properties, with no direct measurement to confirm exactly where it actually lay or what crossing it would actually be like. That changed in August 2012, when NASA's Voyager 1 spacecraft, launched all the way back in 1977 on a mission originally intended to study only Jupiter and Saturn, became the first human-built object to definitively cross the heliopause and enter true interstellar space. Detected through a dramatic and unmistakable change in the density and type of particles, the spacecraft's instruments were recording as the outward-flowing solar wind plasma gave way abruptly to the colder, denser plasma that fills the space between star systems. Its twin, Voyager 2, launched the same year, but on a different trajectory that took it past Uranus and Neptune as well, followed it across a similar boundary in 2018, providing a second, independent confirmation from a different location around the heliosphere's edge. Both Voyager spacecraft, now well over 4 decades into their mission, and still, remarkably, transmitting data back to Earth using power sources that continue slowly decaying, remain the only human-built objects ever to have physically left the space directly influenced by the sun's outward-flowing wind. Their journey, and the striking data they continue to send back from a region no other spacecraft has ever reached, offers a useful reminder of scale that's easy to lose amid discussion of flares and storms measured in mere minutes and hours. The sun's influence, its heliosphere, its magnetic reach, extends across a volume of space that took the fastest, most enduring machines humanity has ever built more than 3 decades of continuous travel to finally leave behind. And even now, sitting in interstellar space, both Voyagers remain, technically, gravitationally bound to the sun, orbiting it on trajectories so vast they won't complete even a small fraction of a single orbit within the remaining functional lifetime of either spacecraft's power source. The Halloween storms and other close calls. The Carrington event of 1859 and the near miss of July 2012 are, by a meaningful margin, the 2 most frequently discussed episodes in the modern history of solar storms. But they are far from the only significant entries in that history, and the events sitting between them offer their own instructive lessons about exactly how this kind of risk actually unfolds in practice. In late October and early November 2003, the Sun produced a remarkable, tightly clustered sequence of major flares and coronal mass ejections, several of them among the most powerful directly measured by modern instruments, in an episode that came to be known, somewhat informally but memorably, as the Halloween storm. One of the flares in this sequence, as mentioned earlier in this documentary, was powerful enough to overwhelm the sensor of the primary satellite designed to measure such events, leaving its true peak intensity likely somewhere in the range of X28 to X45 by various later estimates. Genuinely uncertain, a rare case of a solar event outrunning our ability to directly measure it. The associated geomagnetic storms disrupted satellite operations worldwide, forced airlines to reroute a number of polar flights to avoid radiation exposure to passengers and crew, and temporarily knocked out a satellite, with power outages reported in Sweden. It fell well short of Carrington-level catastrophe, but it offered a clear, well-documented, modern demonstration of the Sun's ability to produce genuinely disruptive space weather with essentially no advance notice beyond the roughly 1-day CME travel window, reaching further back. And relying on more circumstantial but still compelling evidence, some space weather historians have pointed to a powerful geomagnetic storm in May 1921, sometimes called the New York Railroad Storm, as a plausible contender for the second most intense event of the last century and a half, based on the surviving magnetic measurements and newspaper accounts of the period, which described telegraph and early telephone equipment failures, and, notably, a fire that broke out in a New York Central Railroad control tower, apparently ignited by induced electrical currents in signaling equipment. Because the surviving instrumental record from 1921 is considerably less complete than modern data, direct comparison to Carrington or to 2012 involves real uncertainty, but the event is generally regarded within the field as a serious, historically documented reminder that Carrington-class storms are not confined to a single 19th century anomaly, a separate and genuinely striking case, only connected to solar storms through analysis published decades after the fact, involves a cluster of naval sea mines that detonated, seemingly without any physical trigger, off the coast of North Vietnam in August 1972, during a period of documented intense solar activity. A study published years later by researchers examining declassified military records alongside contemporaneous solar and geomagnetic data proposed that the mines, which had been designed with magnetic triggering mechanisms sensitive to changes in the surrounding magnetic field, may have been set off by the unusually strong geomagnetically induced currents generated by an intense storm passing through the region at the time. An unusual military, rather than civilian illustration of exactly the same underlying physical principle responsible for the Quebec blackout and the telegraph fires of 1859, a rapidly changing magnetic field inducing unplanned electrical effects in equipment never designed to encounter one. What these additional cases, taken together, actually demonstrate is less about any single dramatic event and more about the underlying statistical texture of the risk. Genuinely significant solar storms, capable of measurable real-world disruption, are not confined to two isolated, headline-grabbing incidents separated by a century and a half. They occur with meaningful, if irregular, frequency across recorded history, at a range of intensities, affecting whatever category of contemporary technology happens to be most vulnerable at the time. Telegraph wires in 1859, railroad signaling in 1921, naval mines in 1972, satellites and power grids in 1989 and 2003, and, very nearly, the vastly more electronics-dependent civilization of 2012. A relevant question for the future isn't whether the sun will eventually produce another serious storm. The historical record makes reasonably clear that it will, but which category of modern infrastructure happens to be standing most exposed when the next one arrives, and how well prepared that infrastructure turns out to be. Getting ready. How we prepare. Given everything described so far in this documentary, it would be reasonable to walk away with the impression that modern civilization sits essentially helpless, waiting passively for an unpredictable star to decide its fate. That impression, while understandable, isn't entirely accurate. Over the past 2 to 3 decades, and with real acceleration over the last 10 to 15 years, governments, power utilities, and space agencies have taken concrete, if still incomplete, steps toward reducing exactly the kind of vulnerability this documentary has described. On the forecasting side, space weather monitoring has grown from a niche scientific curiosity into an operational discipline treated with genuine institutional seriousness. Agencies, including NOAA's Space Weather Prediction Center in the United States, now issue regular, formalized watches, warnings, and alerts for geomagnetic storm activity, modeled deliberately on the structure of ordinary terrestrial weather forecasting, feeding data continuously from a network of dedicated spacecraft, including the aging, but still critical Suho Observatory. The more recent Escobar satellite stationed 1 million miles sunward of Earth for early warning, and growing constellation of additional monitoring instruments, into models that, while still far from perfect, represent a substantial improvement over the essentially non-existent forecasting capability that existed even a few decades ago. On the infrastructure side, electric utility regulators in several countries, including mandatory standards adopted in the United States following recommendations that intensified after the 1989 Quebec blackout and gained further urgency following the 2012 near miss, now require many grid operators to assess their vulnerability to geomagnetically induced currents and, in some cases, to install physical mitigation hardware directly on the most vulnerable high-voltage transformers. These devices, generally referred to as GIZ blockers, or neutral current blocking devices, work by inserting a capacitor into a transformer's grounding path, allowing ordinary alternating current to pass through normally during regular grid operation, while blocking the near-direct current geomagnetically induced surges severe storm would otherwise send flooding into the transformer. Deployment remains genuinely uneven across different countries and even different regions within the same country, reflecting the real cost of retrofitting existing infrastructure and ongoing disagreement among engineers about exactly how severe the largest plausible storm might be, and therefore how much protective investment is actually justified. The fact that this conversation is now a standard, funded part of grid engineering and regulatory planning, rather than a niche concern raised only by a handful of specialized researchers, represents a genuine, measurable shift from where the field stood even 15 or 20 years ago. Satellite operators, too, have adapted meaningfully, incorporating radiation-hardened components, redundant systems, and, increasingly, the ability to place spacecraft into a protective, safe mode, powering down non-essential and particularly vulnerable systems temporarily when space weather forecasters issue advance warning of an approaching storm, reducing the window of exposure during the periods of greatest actual risk. Airlines operating polar routes, which pass through regions where the protective effect of Earth's magnetic field is weakest and radiation exposure during a major solar event is consequently highest, now routinely consult space weather forecasts and have established procedures for rerouting flights to lower latitudes during significant events, a direct practical legacy of the lessons learned during the 2003 Halloween storms. None of this amounts to a solved problem, and reputable researchers within the field remain candid that meaningful gaps persist in forecasting precise in the pace and completeness of grid hardening investment, in the sheer scale of a truly Carrington or greater event relative to the scope of current mitigation measures. But the overall trajectory across the last 2 to 3 decades has moved unmistakably in the direction of a civilization that treats this specific risk as a real, ongoing, actively managed engineering and policy problem, rather than the largely unrecognized vulnerability it still was as recently as 1989, when Quebec grid operators discovered the hard way, in the space of about 90 seconds, exactly how exposed their system actually was. Watching the Watcher. Almost everything described across this documentary, the coronal heating mystery, the internal structure revealed by heliosismology, the detailed physics of flares and coronal mass ejections, even the improving forecasts now feeding into grid prod and satellite safe mode decisions, depends on a small, carefully maintained fleet of spacecraft that have spent the last 3 decades doing something no ground-based telescope, however powerful, can fully accomplish: watching the sun continuously from multiple angles across wavelengths Earth's own atmosphere blocks before they ever reach the ground. The workhorse of that fleet, launched in 1995 as a joint mission between NASA and the European Space Agency, is the Solar and Heliospheric Observatory, universally known by its acronym SOHO. Positioned at a gravitationally stable point roughly 1 million miles from Earth, directly between Earth and the Sun, SOHO has provided nearly 3 uninterrupted decades of continuous solar monitoring, watching the corona, tracking coronal mass ejections as they leave the Sun, and, almost as a side effect of its main mission, becoming, through a citizen science program analyzing its imagery, the single most prolific comet discovery instrument in the history of astronomy. having identified several thousand comets, the overwhelming majority of them small objects that approach too close to the sun's blazing heat and are destroyed in the process of their discovery. A more recent and considerably more ambitious mission, NASA's Parker Solar Probe, launched in 2018 and named, unusually, after a still-living scientist, Eugene Parker, the same physicist who first proposed both the existence of the solar wind in the 1950s, a prediction initially met with considerable skepticism before being confirmed by early spacecraft measurements, and later the nanoflare hypothesis for coronal heating discussed earlier in this documentary, has done something no previous mission attempted: fly directly into the sun's corona itself, protected by a specially engineered carbon composite heat shield capable of withstanding temperatures exceeding 1,370 degrees Celsius on its unfacing side, while keeping the spacecraft's instruments tucked in the shield's shadow. At a comparatively comfortable room temperature, Parker Solar Probe has made a series of increasingly close approaches, using repeated gravity-assist flybys of Venus to gradually tighten its orbit, and became, in December 2021, the first human-built spacecraft to fly through the corona and directly sample the material there, an achievement described at the time by NASA as equivalent, in the scale of exploration it represented, to the first landing on the Moon. Complementing Parker's direct, close-range sampling, the European Space Agency's Solar Orbiter mission, launched in 2020, take a different but equally valuable approach, carrying a full suite of remote sensing instruments capable of actually imaging the sun's surface and corona in detail. Something Parker Solar Probe, flying too close and too fast for conventional imaging, cannot do, while also gradually tilting its orbit out of the plane in which all the planets orbit, providing, for the first time in the history of solar observation, genuine images of the sun's polar regions, areas that, from Earth's perspective, and from the perspective of essentially every previous solar mission, have always been viewed only edge-on, at a severe and scientifically limiting angle. Together, this small constellation of spacecraft, aging but still essential veterans like SOHO, more recent close-approach missions like Parker Solar Probe, wide-angle imaging platforms like Solar Orbiter, and dedicated early warning sentinels like DS-SCOVAR, represents the accumulated, hard-won observational infrastructure underlying essentially every claim made across this entire documentary. Comfortable, static picture of the sun that most of us grew up with was built on a comparatively thin foundation of ground-based observation, filtered through Earth's own obscuring atmosphere. A considerably stranger, more dynamic, more dangerous picture this documentary has tried to convey exists only because, for the last 3 decades, humanity has finally managed to put a persistent set of eyes directly in space, close enough and continuous enough to watch the sun actually behave the way it really does, rather than the way it merely appears to from 93 million miles away, through a haze of air, not a spatial star. For all the drama contained in this documentary, the flares, the storms, the corona's unsolved heating mystery, the eventual red giant expansion, it's worth pausing to place the sun honestly within the broader context of the galaxy it belongs to, because doing so reveals something almost humbling. By the standards of stars generally, the sun is remarkably, deliberately unremarkable. Astronomers classify stars using a system developed and refined across the late 19th and early 20th centuries that sorts them by temperature and, closely related, by color, into a sequence of spectral types labeled O, B, A, F, G, K, and M, running from the hottest, most massive, and most brilliant blue-white stars down to the coolest, smallest, dimmest red ones. The Sun sits solidly in the middle of that sequence, classified as a G2V star, a G-type main sequence star of a specific and comparatively narrow range of temperature and mass, glowing at a surface temperature of roughly 5,500 degrees Celsius, the same temperature already introduced earlier in this documentary when describing the visible photosphere. Stars of this general type are not the galaxy's most common. That distinction belongs overwhelmingly to the smaller, cooler, dimmer M-type red dwarfs, which are thought to make up somewhere around 3/4 of all stars in the Milky Way. But G-type stars are far from rare either, representing a meaningful, well-populated slice of the galaxy's overall stellar census. In terms of raw physical statistics, the Sun is entirely ordinary among stars of its own type. Its mass, its radius of roughly 696,000 kilometers, its total energy output, and its surface temperature all fall close to the expected values for a G2V star of its particular age, without any of the unusual extremes. Extraordinarily fast rotation, an unusually close binary companion, dramatically higher or lower than typical magnetic activity for its class, that make certain other well-studied stars scientifically interesting specifically because they deviate from the norm. This ordinariness, this lack of any single standout distinguishing feature, is precisely what makes the Sun so scientifically valuable as a benchmark, because we can study it up close in extraordinary detail, and because it appears to be a genuinely representative example of an extremely common category of star. Insights gained from studying the Sun translate with real confidence to understanding countless other G-type stars scattered across the galaxy that will likely never be observed with anything close to the same level of detail. The Sun's position within the Milky Way itself is similarly unremarkable in the most useful sense of that word. It sits roughly 26,000 light-years from the galaxy's center, comfortably within one of the Milky Way's spiral arms, in a region sometimes informally called the galactic habitable zone, not too close to the crowded, energetic galactic core, where intense radiation and frequent close stellar encounters would make stable planetary systems considerably less likely to survive undisturbed across billions of years, and not so far out toward the galaxy's sparse outer edge that the heavier elements needed to build rocky planets and complex chemistry would be in comparatively short supply. Like every other star in the Milky Way, the Sun is in constant motion, orbiting the galaxy's center at a speed of roughly 220 kilometers per second. Fast enough to circle the entire galaxy once approximately every 225 to 250 million years. A single circuit, sometimes informally called a galactic year. Since the Sun formed roughly 4.5 billion years ago, it has completed somewhere between 18 and 20 such galactic orbits, a genuinely difficult figure to hold in perspective against the comparatively minuscule span of recorded human history, which occupies not even the final rounding error of the Sun's most recent single lap around the Milky Way's center. None of this ordinariness diminishes the Sun's importance to the one planetary system that actually depends on it. Quite the opposite. It means that everything learned here, painstakingly, across more than a century of careful observation and theory, from the details of the proton-proton chain to the still unresolved mystery of coronal heating to the statistical uncertainty surrounding potential superflares, represents genuine, transferable insight into how an entire, extremely common category of star across the observable universe actually behaves, turning the sun from merely our own personal, irreplaceable star into something considerably larger. A detailed, close-up case study standing in for billions of broadly similar stars, each one, quite possibly, warming its own planetary system with the exact same mixture of patient, life-giving stability and unpredictable, occasionally violent energy documented across this entire film, Pixies, and the corona's secret stage. Before the age of coronagraphs, dedicated space telescopes, and spacecraft like SU, capable of artificially blocking out the sun's overwhelming glare to observe its faint outer atmosphere continuously, there was actually one narrow, fleeting circumstance under which the corona could be observed at all: a total solar eclipse, when the moon, by a striking and purely coincidental accident of celestial geometry, sitting roughly 400 times smaller than the sun, but also, at this particular epoch in the solar system's history, roughly 400 times closer to Earth, happens to appear almost exactly the same apparent size in Earth's sky, allowing it to block the blinding disk of the sun's photosphere precisely enough to briefly reveal the far fainter, otherwise invisible corona surrounding it. For roughly 2 centuries before the launch of dedicated space-based solar observatories, this brief window, totality, during a solar eclipse, typically lasts only a few minutes at any given location, and sometimes barely more than a minute, represented the single most important opportunity available to solar astronomers, driving elaborate, carefully planned scientific expeditions to remote corners of the globe, wherever the moon's narrow shadow path happened to fall, all in pursuit of data that might otherwise take years to gather through indirect means, or might not be gatherable at all. It was, as already described earlier in this documentary, precisely such an eclipse expedition in 1868 that led to the discovery of helium in the sun's atmosphere, a discovery entirely dependent on the accident of totality, briefly revealing light from the sun's outer layers that would otherwise have remained forever hidden behind the photosphere's overwhelming glare. Eclipse expeditions produced results extending well beyond solar physics itself. In May 1919, British astronomer Arthur Eddington led one of 2 coordinated expeditions, his own team traveling to the island of Principe off the coast of West Africa, a second team traveling to Sobral in Brazil, specifically to test a startling prediction made just a few years earlier by Albert Einstein's newly published general theory of relativity, that the sun's gravity should very slightly bend the path of starlight passing close by it, an effect only measurable during a total eclipse, when the sun's own overwhelming brightness would not otherwise wash out the faint, distant stars needed for the comparison. Eddington's careful photographic measurements, comparing the apparent positions of stars near the eclipsed sun against their known positions when the sun was elsewhere in the sky, found a deflection closely matching Einstein's prediction, a result announced later that year to considerable public fanfare, and widely credited, at the time and since, with transforming Einstein from a respected physicist within his own field into a genuine global celebrity, all made possible by the same brief, precious window of solar totality that had revealed helium half a century earlier. The age of continuous space-based coronal observation, beginning in earnest with missions like SOHO in the 1990s and extending through Parker Solar Probe's direct sampling in the 2020s, has considerably reduced solar physics' dependence on the rare, fleeting circumstance of a total eclipse. Researchers no longer need to wait years and travel to often remote and logistically difficult locations for the handful of minutes of natural totality that used to represent their only opportunity to study the corona directly. But eclipses have not become scientifically obsolete, even in the modern era. Certain coronal features and certain wavelengths of light remain more cleanly observable during the genuine, unobstructed conditions of a natural eclipse than through any artificial coronagraph, which must always block out a somewhat larger portion of the sky immediately surrounding the sun's disk than the moon does. In order to compensate for the imperfect optics of an artificial occulting instrument, and inevitably obscures a corresponding band of the corona's innermost, scientifically valuable region in the process. There is something quietly fitting, in the context of everything else this documentary has described, about the fact that our species' first real glimpse of the sun's true, violent, magnetically tangled outer atmosphere depended entirely on a coincidence of orbital geometry. The moon happening, purely by chance, to appear almost exactly the same size in our sky as the sun itself. A coincidence with no deeper physical necessity behind it, no reason it had to be true, and one that is itself slowly, imperceptibly changing as the moon continues its gradual multi-centimeter per year drift away from Earth, meaning that many hundreds of millions of years from now, total solar eclipses and the brief accidental window into the corona they have provided humanity for the whole of recorded history will eventually become permanently impossible. The moon, having drifted too far to ever again fully cover the sun's blazing disk. We began this story with the picture most of us carry without examining it. A calm yellow disk, dependable as a clock, quietly warming the world from a comfortable, unthreatening distance. We end it somewhere considerably stranger. A ball of plasma, 1.5 million kilometers across, powered by a nuclear reaction so inefficient it barely outpaces a compost heap, so vast it still floods an entire solar system with light. Star, whose visible surface boils in million-kilometer convection cells, whose outer atmosphere runs, for reasons still not completely understood, hundreds times hotter than the layer beneath it. A magnetic field wound tighter and tighter across each 11-year cycle until it snaps, releasing bursts of energy capable, on the right trajectory, and the long day of darkening cities, grounding satellites, and pushing the recovery timeline of modern infrastructure into genuinely uncomfortable territory. None of that makes the sun something to fear in any simple, paralyzing sense. It makes it something to respect properly, the way earlier civilizations, without a shred of the physics we now have access to, seem to understand instinctively, treating the sun's continued good behavior as something worth watching for, rather than something owed to us by default. A comfortable picture of a calm, unchanging sun was never really a description of the star itself. It was a description of how rarely, across one particular human lifetime, its true nature has happened to interrupt our daily routine. That is quietly, genuinely changing. We now have spacecraft flying directly through the sun's corona. We have satellites stationed 1 million miles sunward of Earth, watching for the specific magnetic signature that determines whether an incoming storm will graze past harmlessly or strike with real consequence. We have decades of accumulated data, slowly refining our still imperfect ability to forecast the rhythms, if not yet the individual violent moments, of the star our entire civilization depends on. None of that erases the underlying uncertainty this documentary has tried to describe honestly, without either exaggerating or minimizing it. But it represents something our ancestors, watching the same star with nothing but careful eyes and older, unprovable stories about gods and chariots, never had. The beginning of a genuine, evidence-based understanding of exactly what it is we're living beneath. Consider everything that had to be discovered, painstakingly, piece by piece, across a century and a half, just to arrive at the picture this documentary has laid out. A conservative German mathematician, noticing dark lines in scattered sunlight, unable to explain them. A pair of astronomers, staring through eclipse-darkened skies in 1868, finding an element that didn't yet have a name on Earth. A physicist buried a mile underground in a converted gold mine, spending 3 decades chasing a discrepancy in ghostly particles that turned out to reveal an entirely new property of nature itself. An unassuming British astronomer in 1919, comparing photographic plates from an island off the coast of Africa, confirming that the sun's gravity could bend the path of starlight, and in doing so, handing Albert Einstein to the wider world. Spacecraft launched in 1977 to study Jupiter and Saturn, still transmitting data decades later from a region of space no human instrument had ever reached, quietly redefining where the sun's true influence actually ends. None of this knowledge arrived easily, or all at once, or without long stretches of confusion and false starts along the way. It was built the way all durable scientific understanding is built, slowly, skeptically, one stubborn anomaly at a time, by people willing to sit with not knowing for years, sometimes decades, before the picture finally came into focus. And the picture, even now, remains genuinely unfinished. Coronal heating problem, despite Parker Solar Probe's extraordinary direct measurements, still doesn't have a single, universally agreed upon final answer. The question of whether our own sun could someday produce a superflare vastly beyond anything in recorded history remains a live, contested question in the scientific literature, not a settled one. The precise fate of Earth's orbit during the sun's eventual red giant expansion, swallowed entirely or spared by a narrow, uncertain margin, cannot yet be stated with full confidence by the best models currently available. Good science, done honestly, doesn't always resolve into tidy, closed conclusions, and a documentary that pretended otherwise would be doing this subject a real service. Part of truly understanding the sun, at this point in our species' relationship with it, means becoming comfortable holding open questions alongside the ones we've already answered, treating uncertainty itself as useful, honestly reported information, rather than something to be smoothed over for the sake of a cleaner story. There's a particular kind of vertigo available to anyone willing to sit with the timescales involved in this story, and it's worth allowing yourself to feel it, at least once. The sunlight touching your skin today began its journey as fusion-born photons trapped in that impossibly slow random walk tens of thousands of years ago, before agriculture, before writing, before most of what we'd recognize as human civilization had even begun. That same sun has completed something like 20 full orbits of the Milky Way's center since it first ignited, a span of time in which the entire history of life on Earth, from the first single cell to this very sentence, occupies a sliver too thin to meaningfully register. And the same star responsible for that sunlight, that orbit, and that entire unbroken chain of life will, on a timescale still comfortably longer than all of human civilization's past, put together, eventually swell into a red giant, engulf its innermost planets, and end, gently, as a slowly cooling white dwarf, a fate already, in some sense, written into its physics from the moment it first began fusing hydrogen 4.5 billion years ago, unfolding now exactly as gradually and as inevitably as everything else this star does. Held against that scale, the flares and storms and near misses documented across the middle of this film the Carrington event, the Quebec blackout, the July 2012 close call start to look less like isolated headline events and more like exactly what you'd expect from a star this large, this magnetically active, and this old, sitting this close to a species that has only very recently, in the sun's own terms, become sophisticated enough and electrically dependent enough to actually notice and be affected by its ordinary behavior. We are not living through an unusually dangerous chapter of the sun's history. We are, for the first time, simply paying close enough attention and depending on delicate enough infrastructure to actually register what the sun has been doing patiently, continuously, the entire time. The sun isn't what you think. It is wilder, more violent, more inefficient, more paradoxical, and more precarious than the calm yellow disk sitting in most of our imaginations. It is also, in the same breath, the specific, irreplaceable reason there was ever enough time, enough warmth, and enough patient stability for a small blue planet to grow anything as improbable as a forest, an ocean current, a mind capable of building a telescope and pointing it, carefully, filtered, and shielded, back at the very star responsible for all of it. Worse than you think. It's also, somehow, exactly enough.